Good morning. So it's my pleasure to introduce the NeuroMem technology from General Vision. General Vision is the inventor of this technology that originally came from IBM, and it was called the ZISC. Since then, we've been supplying neuromorphic chips since 1999, and we've developed also an ecosystem, including board drivers and tools. So we are the owner of the IP, which can be translated into an ASIC or an FPGA. We designed two chips. So in 2008, it was the CM1K that we designed with Oki Semiconductor. They manufactured it for us, and this chip had 1,024 neurons and a little extra, including a video recognition logic to interface directly with a CMOS sensor, and an I2C controller for low pin count connectivity. And this was done in 130 nanometer technology, so it ended up being an 8x8 chip, which was quite big for today's standard. So in 2016, we found a partner with Nepes in Korea. We designed a new chip for them with 576 neurons. No extra logic or communication, and it ended up being a 4x4 millimeter chip, very small, designed in 110 nanometer technology and packaged as a wafer scale package. So that is very convenient to do SoC and multi-chip module and so on. We also licensed the technology in 2011 to several companies, but the most important one was Intel. And Intel made a chip, actually put the IP in a QuarkSE chip that they marketed also in the form of the Curie module. This was released in 2016. So you can see here the diagram of the specification of the Intel QuarkSE, and what they call the pattern recognition accelerator is actually in the NeuroMem IP. I forgot to mention that NeuroMem stands for neuromorphic memories. It can be also qualified as intelligent memories and also neural networks. We'll cover that in the presentation. I'll start. So this technology is not brand new. And I'll start, I'm showing here a picture of a system that we did in 2003. That's the first system that we designed jointly with Guy when he came on board General Vision and brought this technology to the company. So you can see the customer in this case was the manufacturer of a filleting line, and he was installing these on boats. So it was a great fielded application for us, because the best proof that the neurons can be trained simply by the fishermen and adapt to the different type of expedition they were doing at sea. No connectivity to the cloud didn't exist actually in 2003, and no connectivity to the network. Basically with the neuron they could easily adapt. And to make a long story short, what happened is when they installed the Zcam camera with the neurons, and they started an expedition in Norway. It was in December, and they called us. At one time, the fishermen were kind of lost because the system was not working anymore. And they have forgot to tell us that the fish do not have the same scale in summer and in winter. And they were kind of panicked, but we just had to tell them to learn a few more examples of fish captured at winter time. So it expanded and reached the knowledge they already had, and from there on they had a network that could recognize fish at all time of the year. So that was a great example for us of adaptive learning and lifelong learning. So the technology was not born yesterday, but unlike silicon technology, which usually after a few years become obsolete, well, it turns out that the NeuroMem technology has never been more relevant than today. This is because of the proliferation of sensors that are everywhere, the big buzz about artificial intelligence, deep learning, the storage that is becoming increasingly massive. So we really have a need for neuromorphic technology to do always-on pattern recognition with lifelong learning, and also with a realistic speed performance. So I'll go into a little more detail about this always-on pattern recognition. In the neurons, we can use them at different levels, starting from the simplest, just a simple identification, what's the closest match from a stimuli. The stimuli can come from any type of data, it can be sound, vibration, image, text. Then for some application, you may want more detailed classification, including also some ideas of confidence factors of the neurons. Basically, it gives you how close an input stimuli is from models that have been learned before. And finally, the most important in industrial predictive maintenance, for example, is the ability to detect anomalies and novelties. And this is a unique feature of the NeuralMem technology compared to existing neuromorphic chip or neural network chip that most of the time will give you the closest answer, but will not tell you when they do not recognize. And what is very important everybody knows that if you think you know everything, you'll never learn. So by not having the ability to acknowledge an unknown, an anomaly or novelty, you cannot enrich your knowledge. So that's why we can claim that we're capable of lifelong learning on the chip itself. We don't need connectivity to an external CPU, processor, or even the cloud to do additional learning. Again, the example of the fisherman was great for us. Lifelong learning is also essential for adaptivity and practicality of artificial intelligence. If we want intelligence at the edge, we need this type of feature. Finally, with lifelong learning comes the question, what happens if I run out of neurons? The neurons basically will hold your knowledge. They're gonna accumulate the models that have been taught. And after a while, they're going to be filled in the chip. Again, in the NM500, we have 576 neurons, which means we can store 576 models. If you need to fine-tune your knowledge and add more examples, well, the NeuralMem technology has a unique architecture which allows to cascade multiple chips. And without any impact on the controller and the software that was designed. It's not like a memory bank where if you expand, the bus expands. In the case of NeuralMem, the bus width is fixed. So you run out of neuron, you just stack some more, and you double the capacity of your network and so on. Later on in a slide, I'll show an architecture where we had over 65,000 neurons stacked together. So basically, if your knowledge expands, we're here to sell neurons and we'll easily fulfill that demand. The last point is about deterministic latency, which is very important also. As you commit more neurons, expand your knowledge, you could suspect that the response time is going to deteriorate. Well, again, thanks to the unique parallel architecture of the NeuralMem technology, this response time is constant. And today it's in the order of microsecond. I say today because with the two chips that we currently have, the CM1K and the NM500, which I mentioned earlier, and this has to do with the clock speed. We run at 27 megahertz and the other one at 36 megahertz. So the reason why we don't have to go in the gigahertz speed is because all the neurons work in parallel. It's a unique parallel architecture. So working together, we don't need to go into high speed to get a response in microsecond delay. Also, this latency is the same for recognition and for learning, which is also very important. I'm going to launch a video that illustrates the use of neurons to do an image-to-speech demonstration. It's battery operated, so we used in this case an FPGA from a lattice with some neurons on it. You can see that, so you can see the battery. It's connected to a microphone, and so Guy, my partner, is doing the demo, and he has just 4 push buttons in his hands to indicate, to basically teach the categories of the play card we're going to show. So it's very simplistic, but it really shows the real-time learning capabilities. So I'm going to learn the movie now. Actually, So this is a description of the equipment we used. Again, very simple, battery operated. The stimuli is a CMOS sensor. Input is gig pushing the 4 buttons. Output is a speaker. Okay, so this is a very simplistic demonstration. Oops. Okay. I want to mention that when Intel came out with the Quark SE and the Curie, it was very beneficial for us because they introduced a board called the Arduino 101, which is very low cost. So it gave us the ability to introduce our NeuralMem technology to all the makers community and developers at very low cost, and that's what this demo is based. The number of different categories that you can learn in a NeuralMem chip is actually up to 32,000 different categories, so there is lots of space. In this type of demo with a manual supervised learning, we limited ourselves to 4, but you can go way beyond that. What else to say? So let's continue. So when we describe the NeuralMem technology, it's basically a combination of associative memory and also a trainable neural network. So that makes a neuromorphic memory. The recognition part, so it's made by association. It's kind of like a content reactive memory, except that it's a memory that have no address, or content addressable memory, but with no address. Again, because all the memories are accessed in parallel. A neuron is really just a memory with some recognition logic around it. The recognition can be performed, we can request to have an exact match or a fuzzy match, because the neurons will fire also if you have similarities between an input stimuli and the model that they hold in their own memories. And it's possible, like I mentioned earlier, to have this notion of unknown or uncertainty, which is very important. So if no neuron fires, it means that the input stimuli is not recognized, and then we can decide to either learn it, or it's, in the case of a predictive maintenance application, that's going to trigger, for example, a warning because we have, for example, a defect showing up in a part or something like that. The notion of uncertainty is also very important. The neurons can be trained using different feature extraction. So I'll take the example of image recognition. To classify an object, you may want to use its overall shape, but also add a classification based on its texture, graininess, and its color. So it's very possible to decide to train the neurons on these different features separately. And in this case, that's what we call the context. So some neurons will be trained on the color context, shape, texture, for example. And if you show a new part or a new event or scenery, and that one context does not properly recognize or give you signs of uncertainty, some neurons fire and are not in agreement with a recognized category, that give you the ability to decide to, instead of applying a decision rule, to trigger another context and see what the neuron of this other context will recognize. So basically, you're enriching the way the diagnostic is going to be made, and you can make a more robust decision. This can be very important, for example, in medical imaging, where the cost of the mistake can be important. The trainable attributes of the neural net technology, so they learn by example, like any neural network, but they have a built-in adaptive model generator. And built-in, I mentioned earlier, the training is really done on the chip itself. The model generator means that the neurons, when a new input stimuli is broadcasted to them with a category to be learned, they will first run all together a recognition, make sure none of them already recognize that pattern. If it does, then they're just going to discard the learning instruction because what's being taught is already known by the network. So that's what I mean by intrinsic deduplication. It's fully optimized. There is never two neurons that hold the same pattern and the same category. The way the learning is done can be supervised or unsupervised. The little movie I showed earlier is obviously a supervised demonstration where you have an operator teaching what has to be recognized. There are some unsupervised methods that we called, for example, building the code book. And so all that, we developed some tools and some software that illustrates how to use or to deploy this unsupervised method. The idea, for example, is that since the neuron can autonomously detect novelty and similarities, they can very well be used to cluster and auto-segment the inputs, basically automatically categorize the input that are submitted. Another important key feature is the traceability of the knowledge. The neural networks, the neurons are not like a black box when they've been trained. We can actually export the knowledge, and we can have also an idea when a neuron fires, recognize the stimuli, which one it is, and we can actually read back what is held in his memory. So we can actually really trace how the knowledge has been built. And for the little stories that we had a customer at one time, it's a way if a customer calls and say, oh, it's not working, we can pull out the knowledge and sometimes detect some errors. If the teacher makes a mistake, then the knowledge and the neuron, they're just like a parrot, they're going to reproduce the mistake. And finally, the knowledge is portable. So in the case of the fisherman, if I go back to that, they train on one line. In the boat I showed you had 5 of 6 filleting lines, so they didn't have to train the 6 lines separately. They train on one camera on one line, and then after they just had to save the knowledge, basically the content of the neuron, on an SD card or USB dongle, and transfer it to the other cameras. This is how we represent our neurons. It's to emphasize the fact, again, that it's a parallel architecture. So each neuron is kind of dangling on a bus that we call the neural mem bus. They all receive the same instruction from an external controller at the same time and execute this instruction simultaneously. So the instructions are very simple. Basically, you're going to broadcast a stimuli, which you also call a pattern or a vector. And each neuron will first decide if it's belonging to the activated context, and then compare this stimuli to the pattern that it has in its own memory. On the picture here, the memory, you have to realize the memory takes 90% of the size of the neurons on silicon. It's the most important part. And then all the other register, the context categories are handled by the recognition logic of each neuron. The neurons are all identical. The only thing that will differ is the pattern they're going to hold in their memory, and obviously the category values, which is the tag or the label that's assigned to it at the time it's learning something. So the benefit of the parallel bus is need for a low clock frequency. We have this deterministic latency, which is very important and in the order of microseconds. So whether you have to compare one stimuli to 10 models in 10 neurons or 100 models or 10,000 models, you know that you'll get the response of the closest firing neurons in 3 microseconds. So the same thing for learning. Whether your actual network already holds 100 models or 1,000 models or 10,000, to add a new model to be learned will take also the same order, 3 microseconds. From a hardware standpoint, this parallel bus also brings the fact that it's a fixed bus width. So for designers, it's very easy to design hardware where you can expand the network at will. What Nepes did on they designed an Arduino board called the NeuroShield, and on each NeuroShield you have a little expansion bus just to add a plug-in modules which has some extra NM500 chip. So each time you double, you expand the capacity of the network by 576 neurons at a time. So that's also what I mean by easy scalability. And this bus is the same to interconnect the neurons inside a single chip or across multiple chips. So from a software standpoint, nothing's changed whether you're accessing a chain of 100 neurons, 10,000 or a million. There is no need to handle addresses and index, and there is no supervisor. So that's why it's really highly scalable. So the interface to the NeuroMem is very simple. The type of interaction will be, so first of all, they can handle text information or measurements or genomic data, financial data. They can also receive stimuli from signal, vibration, audio, or from images, video. And this, what we call raw data, has to be assembled into a pattern through a feature, what we call a feature extraction. And this feature extraction here will provide the stimuli to the neuron. So in terms of instruction, it's just a matter of broadcasting the stimuli to the neuron. And the next action, you have the choice either to teach by assigning a category to this stimuli, or recognize it. And so teaching is assigning a category, and recognizing is actually reading out the category of the neuron which fired. Unlike other technology where the neurons are spiking, or digital neuron, we call their action is called firing. And the neuron fires when the input stimuli basically falls within his influence field. The response can be a little more sophisticated than just a category. We can also request the neuron to provide its confidence factor, and that's also basically it's an idea of the distance between the input stimuli to its model. So we can interpret that as a confidence factor. And also we can ask for the neuron to identify itself and provide its identifier. So that can be of interest in the case of tracing how the knowledge is built. Now the output of the neuron can be an alarm. On industrial inspection application, it can be directly connected to a conveyor. That was the case, I forgot to show it in the video in the fish. The output of the neuron was actuating directly the brush that would decide if the fish was an accept, a reject, or recycle. And an accept, for example, was the idea that the fish was the right species, it was in good shape, and in the proper orientation to enter the filleting machine. So within this feature extraction, there are multiple criteria that can be embedded. The teacher, the fisherman in this case, just had to show examples, and the neurons would automatically classify all these multiple features at the same time. Another type of output can be obviously selective transmission or storage of the recognized data. And again, we can save and restore the knowledge built by the neuron for portability and traceability purposes. So the API is really simple, and General Vision has some tools available for more sophisticated interface. I have next a few slides regarding the application. They can be divided, I divided them per type of stimuli. So starting with a sound, one-dimensional sound signals. So they can come from vibration, biosensors, temperature, and so on. And this illustration shows a decision space, for example, that could be built by monitoring how an engine is working. So if we assume that we had three input measurements, like a voltage, a torque, and a vibration, using these three measurements, that becomes a stimuli for the neuron. We could classify them as, so if a stimuli falls within this region, it's going to be a normal vibration. If it falls in this area, it would be a high vibration. But this little red dot is this idea of anomaly, unknown. So if a stimuli falls in this area where no new neuron is covering this area, it's an unknown. So it can trigger, okay, that's a novelty, what do we do with it? Or that's an anomaly, and then we turn out an alarm light or something like that. So the learning with a signal, usually it's comes down to supervised learning of a normal mode of operation, and then we can set the neuron in a mode where they'll do unsupervised learning of novelties. That's a very important feature for predictive maintenance. So because the chip, especially the NM500, is so small, 4x4, we can envision to put it right even next to a ball bearing. Usually there'll be an interface between the sensor itself and the neuron, and that's in an FPGA. And the FPGA will do this feature extraction and read out the response of the neuron to actuate or to transmit, so on. So at the end, the sensor can become really intelligent by actuating, or by also transmitting only information when it is of interest. The second big market segment is for vision and images. So we can envision to have sensors like smart photocells, put neurons in industrial cameras, or in more professional systems like DVRs, and do video analytics. And because it's so low power, also we can put into drones or embedded in an embedded system. Like in this case, it's the neurons are trained to recognize if coffee beans are ripe enough for the harvest. They can be taught. The feature extraction, which I mentioned earlier, could be targeted at, for example, identifying or classifying a discrete object. In some cases, the information of interest, like we can think in medical imaging, if you have a fluorescence microscopy or thing like that, it's more the color, identifying different colors. You can focus the training on detecting shapes or alignments of parts. And then there is a very big market for texture and surface analysis that would work for LCD inspection, but also we did a glass inspection for assay glass, wood inspection, material, and all that. This is a really big market, and the neurons are really well suited for that because it's typically very fuzzy. If you have to classify a texture, the best is to show example and show the neuron how to discriminate one texture from another. So again, the type of recognition can be for just a simple identification, pass-fail of a part, more detailed classification when you want to grade, for example, the quality of a texture, or defect novelty detection, and disparity localization also. So basically that's the idea. In an image, we can scan an entire image and detect where some objects are popping up or some anomalies are detected. The last big segment has to deal with text and packet inspection. So in the proof of concept we've done, it's really where we've used the most neuron possible, because usually what we load in a neuron in this case, some experts will build dictionary of words or expression to do latent semantic analytics. That's a type of a proof of concept that we've done in the past. And then we're dealing, in that case, the dictionary can be, it was like over 20,000 words or something like that. So it means, or expression. So it means that you need one stimuli, one expression become one model for one neuron. So in this architecture, we show a board that we call the NeuroStack that was designed by Guy, and on the board we had actually 4 CM1K chips, so a total of 4,000 neurons. And to load a dictionary for latent semantic analytics, we had to stack up to 16 boards together. We can't see on the picture, but in the middle there is a big connector that interconnects all the boards together, so that's this Neuroman bus I mentioned earlier. So, and there is a USB plug here, so we would send, when a tweet is coming in, we parse the sentence, and each word or expression, depending on the parsing we want, is submitted to all the neurons, and then we get in 3 microseconds if one neuron recognizes or not this pattern. So it's a very actually simplistic way to use the neuron, because in this case usually it's exact matching. The fuzziness is not important like we can use it for images. But it's a good illustration of how we can stack neurons and build a network of millions of neurons. And all this for a very low power consumption. What else? We can do some clustering, drift anomaly detection, trending, and prediction. So again, in the architecture on this board, on the baseboard, there is always an FPGA that will know what type of engine to run. Adaptive control, so that's a case of a special case of signal monitoring, and it can be used. So for a human, this is to help a paraplegic control his motion. This person was actually implanted with a motion controller, I guess, and so it's we're trying to use the neuron to make his walk more humanoid, if I can say that. Right now, he's just controlling his how do you call that, walker. But we hope that he'll be able to not to use that in the future. Adaptive control is also very important for robotics and drones. So finally, to conclude, we hope to put NeuroMem chips everywhere, next to the sensors, to give them autonomous actuation, selective transmission, and storage. We can also put them in the IT equipment to make sure that communication is secure. Maybe I'll go back to the 2 slides I forgot to mention. Security is very important here. Another application we've done with this type of architecture is for packet authentication. So again, it's a very simple use of the neuron, it's exact matching, but the idea is that for a drone, before takeoff, it was loaded with a list of encrypted security code, and then any incoming packet during the data transmission we verified at very high speed that it was the proper key to make sure that the origin of the message was the right one. So that's what I mean by secure IT. So we could have neurons there. And finally, neurons in the data center to perform video analytics or any custom search engine on text, image, or sound. Okay, thank you.